Did you try to simplify the first one?
Yep.
Yeah.
Didn't work?
I think we got it.
This one.
Diagram name.
This is just yeah, so A, wait, so this is A, B, or 1, right?
Year one.
So this is just A, right? This is just A.
Well, you got all the other things.
Oh, this as well, right?
Yeah.
So it's gonna be A or C, D, E,
Minus
B.
E. Yeah.
And this becomes A, B, or
Yeah.
B, C, D, like that.
Yep. Now, would it be better to keep it as the one on the left? Easier to build a schematic from, or the one on the
I don't know yet, but the difference should be very minor. So AB is did I ask you to draw in one line? I didn't. Well, that's true. Let's try
If you want to do the tree diagram, wouldn't it be easier to draw it?
Let's see if we can do it one line. Okay, let's see. I don't know yet. Let's see. Take a look at it. A, B, they are in parallel, right?
In series with B, C, D in parallel.
B, C, D, E, right?
Yeah. I don't know stick diagram. We only got that part, right?
Did you guys just start here? The stick diagram for the first one. The second one is.
Wait, what?
Did you just stuck here for the stick diagram for the first one?
No.
That's where it was stuck.
I built the schematic using the PMOS and MOS, and then I built the stick diagram. That's the easier way to see it.
Oh.
You did it.
Yeah. So far,
I didn't simplify it.
Okay. Just from here, right?
Yeah.
Let's see what's gonna happen.
I got A, B not, D, E not, C, D not, all not.
What?
I don't know what I did. I was just trying to get as many.
So it's already in AOI. We already have the bar on top, so you don't need to do a double bar again.
Well, I did the double bar because I wanted everything to be in. I didn't want to have to use any inverters, but I pulled something out weird.
Oh.
I don't know what the hell I was doing.
I think I got it.
Oh, I broke
think
my
that's what
bar
happened.
first, which gave me weird stuff. That's what I did.
Oh, you mean you did it wrong here?
No, I did De Morgan's law.
Oh, here?
I did it at the very first step. Which,
Yeah, you have a bar on the top, so you don't want to do De Morgan's law.
yeah, and then I ended up like adding more bars.
Remember, AOI means and or inverter, right?
Right.
So it's and or inverter. That's it.
Well,
So you want to follow the.
I was trying to get like each one into its own AND gate, so
Okay.
I have to invert after the AND gate.
Got you.
And so
Yeah.
that thought process.
Yeah, I think we can do it from here, but now we are doing it from here, right? Let's see what's gonna happen. Can we make a one-liner for these 6 transistors? So it is literally 2 in parallel and 4 in parallel. So 2 in parallel, we need a 1 output, which means it must be this, right? And then 4 in parallel, what we got for 4 in parallel is like this, right? But you can put this, you can flip it to the top. Is this correct? So we got AB. But remember I told you guys that, right? So 3 in parallel is what? Like this, right?
Yeah.
For 4 in parallel, it's.
Yeah.
So that's why so for the 2 in parallel on the top, the reason I you know, sometimes for two in parallel, you can do this, right? Or you can do this, remember? For two in parallel. But based on the structure here, because the two in parallel is going to output one pin, that's why I prefer this one. Because this one is going to output one pin because you're going to have a neighboring adjacent PMOS here. That's why I prefer this one instead of this one. Because the output is in the middle, and in the middle diffusion is not connected to anything. The PMOSs are here, right? But the middle pin is here. You have a gate. There's no connection, but you do have a connection here. Confusing?
Can I show you?
Mm-hmm. Yes.
So I did the connection between right there,
Mm-hmm.
and then I just connected to C because those are in series, right?
No, that won't be, wait. Yeah, so this is two in parallel, right?
Yeah.
No, that won't be right because these two are shorted together as well.
I did it completely.
You know what I mean? But you don't have that connection. This is VDD. Any of these transistors being shorted to VDD? No. But this one is shorted to VDD. See? That's why, that's what I'm saying here.
Yeah.
That's why I'm saying, when you are thinking about, before you draw it, right, there are two options for two in parallel. Okay, which one you want to pick up? Based on these two structures are in series, that's why you want to pick up this one. Right, because after I introduce VDD from here, then these two ones, I know one is going to be, is a one-liner, so this one is already shorted to the neighboring PMOS. I couldn't change it. That's why I want to utilize that pin here. That's why I want to use this two in parallel structure. Like, and so this pin here is this pin. Okay, and then you can start from that one and do a four in parallel structure like this. See, it's better to flip it to the top. I didn't do that. Anyway, you know what's going on here. If I flip it to the top, it's going to work as well. Yeah, if I do that, right? So this one has 1, right? 2, 3, 4, and merge to 1. 4 in parallel. This is not easy, right? This part. I don't have to.
Yeah. So I can simplify all of it.
Mm-hmm.
Is that correct?
So you used this one?
Yeah. I feel like it makes the state diagram
let's take a look. That's a NOR gate, so we got these in parallel in this one. Yep, this is right. And you have B in series with everything in parallel. Yep. And then you start from here. So do the A first?
Yeah.
A is where? A is this one?
Yeah, I wrote
A and B. This is B, right?
Yep.
A first and then 3 in parallel, no problem, right? And then short it and B first, and then you got 3 and 1. Yeah, that's good. No problem with this one, right? Let's see.
Now I can do it.
A, B, C, D, E, F. A, B, C, D, E, F. Wait, A, B, C, D, E, F.
Just that one problem, prompt B, we spent 3 days working on it.
Well, I've just been doing it like completely wrong this whole time. This is the issue I'm realizing. Like I just fundamentally was conceiving part of it.
But keep in mind, so it's usually you are keep using these kind of conclusions.
Yeah, I just,
Do more
the
practice on this.
whole connecting the drain sink for me like wasn't clicking when they're. You'll see when you go through my homework and see how poorly I did it.
But definitely review and practice this during over the weekend.
Yeah.
Otherwise, it's
I mean,
just losing points. How could we do this? So 3 in parallel, and then in series. How do we do that? So we are trying to find this kind of structure. And if we do that, yeah? Perfect. That's it. Just saves a lot of time. Let's verify. You want to verify it? 1, 2, merge. 3, merge. So this is here. And then from here, you got 3 in parallel, right? 1, 2, 3. And all merge in one point.
Let's go.
Okay. Any other questions before we move forward to adders?
I have a question about the homework that we just got back.
Yeah.
I feel like, I ran the simulation, I might have done it wrong with the calculation we did in class. And I wasn't getting a switching point voltage or two.
Oh yeah, the calculation was okay, but there was one thing I
couldn't get that with the 3 that we had. I don't know if anybody did you get it right, Jason?
The simulation?
The calculation.
No, it did not.
you were very close on that. You were
so I did the
pretty
math
close.
completely wrong, and it was super close. But I did that after I tried the what we did in class, and it wasn't even close. I think.
See, here's one. I don't know if that one affected or not, but
yeah, we're looking at this.
see here, right? The reason so whenever beta over beta p is very close to 1, the result is very close to 2.5 volts because we are considering 0.8 and 0.9 starter voltages are very close to each other. Yeah. So that's why when this term becomes 1, so you can cancel out VTHN and VTHP. Is that correct? No, if this one becomes 1, right? If this one becomes 1.
How can that one become 1? Because we have 120 over 40.
But that's why we need a bigger width for the PMOS to make it equal, right?
Yeah.
But I'm just saying, like, why when this equals to 1, this becomes 2.5? Right? I'm just doing a really quick calculation. I just don't just trying to find out like 0.9, 0.8, what's the difference over this. It's minor difference. Whenever you're calculating analog, I don't know if you guys are doing that really quickly or calculating like 2.45 is different from 2.6. It's not making sense a lot of times. In analog, usually you just look at the numbers, even though it's inaccurate, you can still find out the gains just by eyeballing it. Yeah. You don't have to calculate into every single detail. So for example, this one, all right? So there's no problem with this equation. VSP equals this, no doubt on that, right? So let's assume this guy is 1. Okay, so the whole term here becomes VTHN, no problem, right? Because 1 times VTHN is still VTHN. Yeah. And if we assume 0.8 equals 0.9, if we assume 0.8 equals 0.9, very close. We're just ignoring the 0.1 difference over there, okay? So these two terms are canceled out. right? So you have nothing left for the things here. And this one is 1, right? So 1 plus 1 is 2, and VDD is 5, so 5 over 2 becomes, yeah.
I feel like you can't assume that there's.
You can, yeah,
I
let's,
get that point, but when we're calculating how to get the 2.5 switching voltage, I don't understand how we got.
oh, here,
It equals, I understand that, but when I'm simulating that, I wasn't able to.
that's why I didn't take points off. Did I take points off from that problem?
Yeah.
I didn't.
For the math you did.
I know I didn't. I didn't take points off. Look at it. How many points? I didn't. You messed up with something else. I didn't.
No,
Oh, yeah, I don't know.
Yeah, I'm going to talk about that later. But let's come back to this one, right? Let's do one by one, all right? No problem. You pay the tuition, so I'm going to explain everything. All right, let's come back to this one, okay? So remember, I roll 3WN over LN equals WP over LP, and I crossed out this one, put a 3 here, which was wrong. So at the very first time, I made it right, actually.
So
I already wrote the,
simulate that value, should be 2.5.
yeah, I already wrote down the comments over there for the correct calculation. You know what I mean? If you want a beta n equals beta p, you must have 3 times, which means you need a smaller n channel and bigger p channel. The PMOSes are having holes, and the majorities they're moving slower. So that's why we need a bigger one, stronger one.
But why in the simulation was the switching point simulated when they're the exact same? Like for me when I simulated them,
Yeah.
like
But yours is not 2.5 volts.
it was pretty close.
No, you didn't. You didn't probe it. If you probe it, you'll see the difference.
It probably, yeah.
You should probe the middle one, the intersection there.
Right, yeah.
No, the intersection. You need to move the cursor to the middle.
Oh.
You didn't probe it. So you have to probe it and then find out.
Close enough.
That's why it's different. And you made them exactly the same size.
Well, yeah, because I put in the signs that I like calculated here, and they're wrong, and so I was like,
Oh yeah.
screw this, and I put in the same size, and it was close, and I was like, that's good enough, I'm done.
Yeah. Anyway, so that's why I didn't take points off. Is that fair? Because I made a mistake on the note. Make sense?
Yeah.
All right. And then the transmission gate. You guys are making the same mistakes. If you have a conclusion, how do you trust each other? Like that's the correct answer. You gotta ask me first.
Well, you saw yesterday, we kept coming up to you.
Well, what happens is I come in with an answer, and Max looks at me like I'm an idiot for having that answer. And so he's so confident in me being an idiot that I believe that he's right.
And you didn't even look at notes. I drew the schematic for you guys.
I
didn't understand it.
Yeah.
Yeah, let's see. And you are going to use it. So you're going to use it for the lab sooner or later. So I'm going to spend some time here real quick.
Do what?
No.
No.
You did it differently.
I did it different than you guys, but still wrong.
Just different in a different way to be wrong.
So it's just an awesome people.
It's not the national flag for Switzerland. You just make sure.
You guys,
No, I know. I didn't know that.
No, we agree with you on that. It's just online is different.
Yeah, when you Google,
Oh no.
they have completely different schematics.
Don't always search the online stuff.
It was 2 inverters, and that was it.
There are too many bad professors in the world. Just don't trust.
Professor Brady.
No, my mistakes were because Dr. Lee's photo was bad. That wasn't about me.
What about this? I drew this one for 3 times
I
already.
drew this on a paper and
Yeah,
did it
yeah,
to
yeah,
you in the lab
yeah,
the morning before the homework was
So it's
due.
just 2 transistors.
Yeah. Do you know these are, so the transistors are 4 terminal devices, right? So this is VDD, right? This is ground. And it's just short these 2 pins. That's it. The 4 pins just shorted that way. And that's the transmission gate. Hey, you got a transistor here, right? This is what you're getting in LT spice, right? Okay. Then you got an NMOS, and you just measure it, right? Flip it. If you don't flip it, it's okay, right?
Yeah.
Why did I ground that pin?
Are we recording?
Just do that. Yes, we are. Yeah. Right?
The only thing we did wrong was to ground it.
Yeah.
And then you're cloudy.
I have to ground this one, and I have to turn on this one, make to transmit anything. That's it. So it's on. If you connect the gates to the opposite way, it's gonna be off, right? If you do that, it won't do anything.
Okay, quick question.
Yeah.
What is the point of this
It's a
when
buffer.
we can just put a wire?
It's a buffer.
Oh, because you can clock it. It's a switch.
This is a switch.
Yeah. Otherwise, I have to grab a scissor. If it's just a wire, you need a scissor to cut it.
Wire it again and
Yeah.
cut it.
All right. So you need a. If you have a billion transistors in the CPU, you need a billion stats sitting in the chip.
So if this is connected to VN, that would be right.
Yeah. You just put it grounded, right?
Yeah,
Ground
I had grounded it. I was like, it's a PMOS. It needs to be on the lowest potential of the circuit. Or NMOS,
Oh.
whatever. And then I grounded it. And then moved on with my life.
Hmm.
So you pass
He gave me a graph that looked pretty close. And I was
Yeah. So yeah, because the PMOS is good at passing. What? No, PMOS.
PMOS is good at passing VDD.
Yeah, NMOS is good at passing.
Right.
Yeah. So if you have these ones, all of them are going to pass, right? Because of that. If you use the pass gate, the PGs, I show the simulation in your homework.
Getting 4 or 5 people in that room talking about moving a transmission gate and none of us could figure it out.
In the
It was
lab?
like-
To be that.
Yeah, we were sitting in your lab. It was the 3 of us, Cheyenne and Calvin.
Oh, they probably forgot it. They
And
did
we
it.
were all sitting there like unable to get LT Spice to do it right.
Oh, interesting. They did it. They did it.
We were in there, we
A year
were
ago.
arguing about it for like an hour.
They did it a year ago. I forgot it.
And Google was telling us something different. It was
Yeah,
chaos.
Google told us it's 2.
2 inverters,
Yeah. That's a double cascade right there.
but you got 4 transistors. It's a buffer.
That's why they were calling it a buffer.
It's a buffer. It's not a transmission gate. It's a buffer.
But they will just pass.
Yeah, it is passing.
But you can't turn it off. Or I guess
You can't listen to gates.
You can't. That's right. You cannot clock it. It's going to be always on.
Yeah.
Because the powers are in the layout. The inverter PMOS and NMOS are being shorted to the rails, right? They're always sourcing currents from the top rail.
So on your schematic for the
Transmission gate.
Yeah, that. The top is source, the bottom is drain. Right?
It's okay. It actually doesn't matter for the
It
C5.
doesn't matter.
For C5, hey, if you open up the layout view, did you see the difference from left to right for the transistor? No,
I don't think.
that's why it's safe.
Okay.
Yeah.
Okay.
no.
If you use one pin as a source, the other pin becomes the drain. Interchangeable in C5, not in other processes. I'm not telling you that, but it's just in C5 for this 40-year-old maybe even longer, 40-year-old technology. It is.
So it doesn't matter when it's oriented in C5, but others it is.
Yeah, for a lot of others, yes. So there's yeah, even for C5.
So your stick diagrams that I make were for technology.
Of course.
Okay, so I used a high voltage HVC5. So even for the 180, if you look at Muse semiconductor, let's take a look at it. I was just browsing some schedules since we just changed the schedule. I'm gonna let you guys know.